So hello again. There was a development that I read a couple of weeks ago about a new smart telescope. These are the telescopes with the built-in camera kind of thing. And they've taken the next step in progressing smart telescope technology and reduce prices. So I thought I'd do a little compare and contrast to what's out there and what these things are. So you've probably seen some of these smart telescopes and went, hey, that's interesting, but $2,000? No. And then they said, well, now it's only $1,000. No, because you look at the parts and you go, that can't cost anywhere near that. And then you look at that next one down, sort of the second row left, and that one's in the $500 range. Okay, but it's from a startup company who you don't know and you don't trust the technology. How can you not have a tube for the telescope? And then a company you do know, ZWO, they came out with the Seestar, their flavor of the roughly $500 telescope, and it's kind of got some depth to it and lens on the front thing, but not quite sure. But if the price dropped a little, I don't know, $400, maybe you'll take a chance on it because you probably spent more than $400 on a good, astronomy, planetary, or deep sky camera. So getting the whole telescope mount head with camera lenses and everything and the software app, take a chance. But if you're one of the ones that came in early and spent $1,000 or $2,000 on them, seeing the price drop below $500 is probably feeling kind of burnt. Well, sorry, I've got to add more salt to the wound because they just went down to the $300 level with more capabilities. Now, this is a zoomed up image of the device, but it's from a company called Celio, and they've got a Kickstarter out there for it. Not a $2,000, not a $1,000, not even a $500 range. It's $299 plus $25 for shipping. The manufacturer's suggested retail price will be $554 once they go into production. But this is a Kickstarter, they're not yet in production, but this is what they're targeting. So if you bought one of those second generation $1,000 ones, there's some things you can't do with it. Not good at planetary, maybe not good at lunar, moon observing, but this is going to do that. And then you've got like the ZWO that it's a $400 range. Good price. ZWO is a reasonable company, but they've actually split Seestar off from the main ZWO company in case either it goes well, they can empower it financially, or if it doesn't work out and they get eclipsed by another company like Celio, then they can sell it out, shut it down, whatever. Celio is kind of the next step in aggregating all these different capabilities into something in the roughly $300 range. It is a refractor, it's not a reflector, and it's actually a 3-lens apochromat. So good color for it. It'll do lunar, planetary, white light solar observing, even terrestrial observing, and it has a USB-C port that supports not only charging its internal battery, but also data transfer so you can hook it up to your computer, as opposed to being anchored to your mobile phone. Interesting capability for something that's lower priced. So how can they make it so cheap? Technology moves forward, the parts are getting less expensive, and they're getting physically smaller and lighter in weight. Plus, there's been a number of product design decisions that also drive down the costs, and software that increases the capabilities. So hardware. I speak occasionally about Raspberry Pi computers. The computer you'd need to run them out is roughly $20 street price quantity one. And it comes with built-in Wi-Fi, Bluetooth, sensor interfaces, camera buses, I2C and SPI. Lots of interface capability for all the sensors and motors and stuff. You can repurpose mechanisms and motors from robotics and drones. So you can get brushless, which are reliable, inexpensive, lightweight, but because drones need higher power props, they have high torque efficiency without using gearing, enough to move a lightweight telescope mount without all the excess gearing that would normally be needed. Lighter weight, more efficient motors, that permits the electronics to run longer on smaller contemporary lithium-ion batteries. You don't need a lead-acid battery to run your telescope anymore. And they're taking not last generation cameras from the mobile phone devices, but current ones. If you need a 4K image, you can get a camera that will do that now. It's cheap, small, high resolution, very good low light, and you can put an infrared filter on it and actually see a bit in infrared without buying a dedicated purpose infrared camera. You can use those for astronomical imaging. Now, the cameras when they transitioned from charged coupled devices to complementary metal oxide semiconductor or CMOS devices, the price of the camera imaging chip really dropped. It went from $400 down to maybe $30. So the cameras got far cheaper. And because the cameras got better, they can do not only 4K, but 4K HDR, high definition, which means instead of getting a million colors or 16 million colors, you get 100 million colors, even better color resolution to go with your APO refractor. You don't need RGB filters anymore. You can do a one-chip HDR color. A lot of improvements in the technology that go into these things, all packaged up into something at the right price point. But what product design decisions did they have to do that really pushed down the cost and increased the capability? They stopped using Cassegrain and Newtonian reflector type telescopes. They went exclusively with refractors. But because the refractor is only like 50 millimeters, half an inch across for the chip, instead of having just one lens or a duplex, two lenses, they now have three lenses for better color resolution. It's called an apochromatic imaging sensor, or an APO. This is what you would get for multiple $1,000 Takahashi or something, but now it's smaller. Because it's smaller, it's cheaper to get three ED quality glass lenses at a low price point. So you get really high quality imaging, high quality glass in an APO at the $300 price level. The next thing is, instead of, if you remember back in the day, bigger telescopes, Meads and Celestrons and such, they had a lot of aluminum forged metal like bodies, and they had bent metal steel tubes and such. That doesn't cost that much money to make each one of them, but it takes a lot of effort to do that. It takes a lot of metalworking and such to do that. This company went with a little more money up front, make everything out of molded plastic, and there's a little bit of upfront cost, but each individual part is far cheaper. And since you can injection mold them, you can make them faster in high volume production. So they're gearing this thing up to make a lot of them. Next thing they went with is altitude azimuth or altitude elevation, azimuth elevation pointing. So it swivels like a Canon or like a Dobsonian mount, not polar or equatorial, which means they can make it lighter in weight because you don't need any counterweight for it, and no tilt plate is required. And they put a receiver screw thread in the bottom of it for the typical 1/4 inch by 20 turns per inch tripod mount. So they just tell you the mount head assembly with the telescope camera and the tube and everything, and then go get yourself a cheap tripod. Whatever height you want a tabletop, you want a full height one, sure, it's going to be something that costs extra, but you can get those on Amazon for well under $100, easy. But because it's an altitude azimuth, there's no Polaris setup, no plate solving. They actually do what Ioptron did many years ago with their cube mounts, and I own several of those, so I know how it works. They take a GPS fix, get time of day, they know exactly when it is and where your telescope is located. Therefore, they know where everything is in the sky. Just wait for it to get a fix. Go to the menu, do a go to. It goes roughly, it doesn't center it in the eyepiece back in the day, but nowadays, since the software is actively imaging, it automatically centers the target because it knows what it should look like. So no plate solving, and even centering is done in software. It's a fast, as the saying goes, telescope. It's an F5, and the imaging chip is low light, which means instead of it having to spend 3 minutes per image and take a stack of images, it can now get the image that you want in a second or less, which means the whole rotation, field rotation of an altitude azimuth imager, not a problem. So no equatorial mount required to get rid of field rotation. And since it's a live image, they just integrate the image and rotate it. You don't worry about field rotation anymore. And date and time, they originally would, like Ioptron did, put a GPS receiver in the mount. They don't even do that anymore. Since you've got an app running on your phone that talks to the telescope, they ask the app, hey, app, go ask the phone where I'm located and what time it is, because the phone's keeping track of your location and track of exactly what date and time are. You don't even need the GPS receiver in the mount. It just goes over and asks your phone, hey, you've just connected to me. What's the date and time? Where are we? It presumes that your phone is nearby the telescope. But because of this, they no longer need one of those coin cell batteries to keep your battery backed up time and date in your mount. This has always been the anathema for go-to telescope owners that didn't have a GPS in them. Every couple of years, you had to sort of open up the telescope and find the coin cell battery and replace the coin cell battery with a new one. And that was mercury batteries. And when they went to lithium batteries, maybe 4 or 5 years, but you still eventually had to replace the coin cell battery. Now you don't even need that. So what are the shortcomings of these smaller smart telescopes that amateur astronomers have had to deal with? Well, there's the old crutches, which are, I don't know if I can live without an interchangeable eyepiece because, I don't know, I spent hundreds of dollars on interchangeable eyepieces and to have just one camera with one set of lenses, I don't know. Removable cameras. I've personally got a camera for planetary and a camera for deep sky, so I have 2 cameras. Having just one camera is like having one eyepiece. I don't know if I can deal with that. And then there's the old adage of, in order to get really good images, you need a big light bucket. Okay, explain to me why a 5-inch, $3,000 Takahashi refractor scope is what the serious amateurs buy instead of like a 16-inch Cassegrain telescope. It's because it's the focal ratio that gives you the better image. The light gathering gives you better detail. And if what you're trying to image is a faraway, distant galaxy, there's only so much detail you can get out of that. But if you're trying to image the moon, which is very bright, you don't need a long exposure duration, but you do need a lot of pixels to get more detail, not a big light bucket. Those big light buckets, they're heavy. And then you have to add on finders and guide scopes and everything comes out heavy. But, it's a manly telescope, not one of these little wimpy things. The original smart scopes would only let you look at deep sky stuff because they were not too good on the positioning and they didn't automatically center. So when it would go to something after doing a plate solve, if it was off by 1/4 of a degree, no worries, go ahead and take the picture. But if you're doing planetary and you're trying to get, a small planet like, I don't know, Mercury or Mars or anything like that, or Jupiter, it's pretty large, but Uranus and Neptune are fairly small. If you're trying to get those, it won't be in the center of your original smart scope. It'll be off to one side. And now you've got to go in and manually adjust it. You could do that, but it got to be old. Can't the software do that for you? Yes, it can. I want to do lunar imaging as well. I want to see the moon. Well, not on a full moon. Pick a sliver moon of some kind, because the original cameras they had in there, the software wasn't smart enough to dim down the camera. So when you had a full moon, the full moon would just look like a giant white orb with no detail because it would bloom. And they had no real planetary capability because they were taking a 3-degree field of view. And by the time you zoom down to something like Mars, it was 20 pixels by 20 pixels. So you threw away too much through cropping because it couldn't zoom up. What if you wanted to do daytime solar? You want to put a white light solar filter on it. These original ones had no provision for doing that. And you go buy an aftermarket filter and sort of tape it onto the front. And it wouldn't be at the right distance. So you get internal reflections and it might move. Glue would wear out eventually. The tape would wear out eventually. So not great. But if the only way you can line the telescope up is by plate solving off of Polaris, you're not going to be doing that in the daytime. And what if you are a birder and you want to take pictures of animals and birds and stuff in the daytime? They had no ability for you to just move the scope around at 0 degrees elevation so you can just look at distant critters, or tilt it up just a little bit. You don't want it to do a go-to, you just want to tilt it up because there's a bird in a tree. So you couldn't do terrestrial imaging. I often did solar observing and planetary observing and even lunar observing in the daytime. So how do you do that in the daytime if the only way you can line up your mount is through plate solving off of Polaris? And even if you want to do it at night, public places have buildings and shrubbery, trees to get in the way. So we can't do plate solving. Getting the location off the phone, the time and date off the phone, and then doing a course positioning to your target, and then letting the software do a fine positioning based upon the image it actually captures, that's far better. This one I I didn't know whether to think of it as comical or I felt sorry for them. I was looking at the latest sort of ballpark 300, 250 to $300 price range item on Celestron's website. Now, you don't get the mobile phone with it, but this is Celestron's latest offering for kind of mobile phone smarts assisted pointing. And that's all it does is pointing. You notice there's no motors on it, so it doesn't track anything. It doesn't do a go-to. You don't have a camera that's looking through the telescope. It's still got an eyepiece on the back. So all you're doing is you unlock the telescope mount, you watch the app, and the app has a like a cursor in the center, and you move the telescope until it's in the center. But these low-end mounts, this particular type of mount, is a bit wiggly. So even if you center it and you lock it, the scope is going to go wonk just a little bit, and it's not in the center anymore. So then you got to use the hand controls to center it. So comparing this at the $250 to $300 range versus that Celio at the $300 range, Celestron's going to find themselves left out in the dust, I think, unless people are just buying by brand name. How to take this even further? I don't think we're done yet. I think that there's more progression here. Now, whether Celio can just do a software update and get some of these extra things, or they have to do like a next generation hardware, like a Celio second generation or Mark II, maybe it'll be less than $200. Eventually, they'll get down to the same price point as low-end optical telescopes, as we would refer to it, the junk optical telescope. You know, somebody will go buy a telescope during the holidays at Walmart for $200, and they're really proud of it, and they would bring it out to the observatory. And I would spend an hour or two trying to show them how to get it lined up, because it was a polar mount, how to get it lined up on Polaris, and then how to swing it over where you can see, I don't know, the moon. And they would look at the moon and go, this is great. I saw the moon in my telescope. And then they would leave and we'd never see them again because they would have to do a polar alignment anytime they wanted to see anything. So it just became something that sat in the closet, or they had it at their street fair and sold it for $1 or whatever. Actually, I had two ladies that came out to the observatory once that they were very proud of their low-end telescope that they spent $1 on in a raffle. Brand new, the telescope was probably $70. But okay, I got them to see it, and they donated $20 to the observatory. So I was happy. You saw that this one has the USB-C connector, which is high current 5 volts. Telescopes like to run on 12 volts and originally ran on car batteries. So if they could find a way to externalize a module that was the battery, it would give the telescope a longer life and permit them to run it, on 12 volts, which easier to get if you're an amateur astronomer community. But if they can make it run off of a 12 volt 2 amp adapter, those are really cheap to come by, and low-end security cameras, those are really cheap for that. So replace the proprietary internal battery with something that's on the outside. Think about your mobile phone. You buy a mobile phone, it comes with a certain level of capacity in the battery. And if you do a lot of travel, you're not going to go buy a phone that has a bigger battery in it. You go buy an external brick that you charge up as an external battery. And then when your phone starts to run low, you have a little cable and you plug it into your phone, and your phone sucks the power off the battery. And then later on, you can recharge the battery. You need to do the same thing for these telescope mounts. Next two things are broader use markets. Imagine you're taking one of these telescopes to a public star party. If you're requiring every member of the public to download some proprietary app onto their phone in order to see the image, because look, folks, there's no eyepiece. You can't I got it on my phone. I'm the owner of the telescope. Looky, everybody come and look at my phone. That's going to get old after a while. What you'd like to do is what I did with a Raspberry Pi, have a public web server inside your Raspberry Pi that's getting images from the camera of your telescope. No proprietary app needed. It's just a web browser. You put out Wi-Fi. You tell them what the Wi-Fi SSID name is and password. They connect to it. They go to the default browser on that site. You have a little menu item that comes up and says you want to see the current image from the telescope, and it automatically refreshes the page. They can tell their friends to, how to do this. When I was at Parkland, we were doing an event for Marjorie Stoneman Douglas. Yeah, we had a bunch of high school students who were all away from the telescope talking to each other about how to get the web interface on their phone, not an app, just browse to the web interface. get that on their phone, and they were all looking at what my telescope was looking at. None of them came over to look at my telescope. And my telescope at the time had two tubes. So it had one tube with the camera and another tube that had an eyepiece. So if people wanted to look through the eyepiece, they can. But if you wanted to, go over in your conclave and talk amongst yourselves and bring it up on the webpage, that worked too. Public star party use where you don't need a proprietary app to see what the telescope is seeing. The next thing is permanent installation. Right now, it's cost prohibitive for a small museum or even a small observatory to put in place a smart telescope. A smart telescope that costs thousands of dollars. Maybe you got enough budget money to do it, but most observatories don't and would rely upon a donation to get such a telescope. But at the $300 level, okay, we can do that. An inexpensive Android tablet, we can get that. That's under $100 nowadays. Supports video out. We can plug it into a TV. And now you can have a go-to telescope mount with a camera in it. You can look at images on a tablet. You can share it via Wi-Fi, or you can put it up on a big screen at the observatory or museum. But you need the ability to run it off of AC power. So you need an AC to DC adapter that you can leave turned on all the time. This would be a great thing for mods to take a look at because it'll do daytime observing as well as nighttime observing. So in summary, smart telescopes are progressing. They're getting even smaller, cheaper, lighter, and this is a particular significant advance of having an APO, an apochromatic refractor. It's not a cheap lens anymore. It's not big and heavy and expensive, and you don't need polar or equatorial alignment. And they can look at lunar, planetary, daytime, and terrestrial. Comes with a bunch of filters, including white light solar filter for looking at sunspots. It's okay to have an app that's proprietary that the owner of the telescope must use to control things. But to just look at what the telescope's looking at, that should be point to a web interface through Wi-Fi that the mount's putting out, and the public doesn't need a proprietary app. And you don't need plate solving anymore. And the app automatically does the fine alignment and tracks. And I think what you're going to see as a result of the capabilities going up and the price crashing down, you're going to see the more expensive folks like the Vaonis and the Unistellar. They either need to come out with a low-end product or get bought up by somebody, or they're probably going to lose market share eventually. Seestar by ZWO, I think they kind of did the right choice to make Seestar its an independent company that ZWO just kind of owns and operates. I think that gives them the opportunity to sell Seestar to Ioptron or somebody who's in desperate need of a smart scope, or to Celestron. So Celestron and Ioptron, because they only want to sell at the high margin, high end, and they've literally gutted their low end. This is going to be the marketplace new low end. And as the low end gets cheaper and far better, the midpoint of the more sophisticated, expensive mounts, the $1,000 to $3,000 range is going to be, why am I spending so much money when for under $500 I can get pretty good? But then what do I know? I own 8 telescopes of various kinds and types and shapes and stuff, capabilities, plus 5 different mounts, again, different capabilities. And I'm still waiting for a better, cheaper smart scope. But the Celio is like a step in the right direction from my perspective. But I've created a smart scope that's my proprietary one that I built based upon a Raspberry Pi. And it was just an inexpensive Maxutov Cassegrain, small diameter. I put a camera in the back, no more eyepiece, and a Raspberry Pi. Took some off-the-shelf astronomy software, put it on there, make it spit out a Wi-Fi interface with a web browser interface. And that was good enough for the high school students at Marjorie Stoneman Douglas. They really liked it. So it's easy enough and cheap enough to do this stuff. I can't see Celio being the last Kickstarter on the low end. And here you can see some of the stuff that I own. And if you're wondering about these companies and these names, there's the Kickstarter for Celio, Vaonis, Unistellar, DwarfLab, that came out with their Dwarf 3, ZWO Seestar, and then Celestron's StarSense Explorer. This was an update on smart scopes. I just see it as a marketplace that is rapidly dropping in price and rapidly increasing capability. Comments? Questions?
In the beginning, you mentioned ED glass. What's ED glass?
When you are making optical elements like lenses, you can make them out of regular glass, which is known as crown flint glass, regular pane glass, or you can make them out of a dispersion glass, which allows you to take more of the light in and pass it through, is basically what you're doing. Because you never notice it, but regular pane glass does not transmit 100% of the light that's coming in. Whereas ED glass is better at transmitting more of the light that enters the lens. And then when you stack these, the reason why you stack the three elements together is the material that the glass is made out of will, like a rainbow, bend the colors of light at a certain angle based upon the index of refraction of the glass material. That's going to fan out, and some of your more UV ended stuff will be bent differently than your closer to infrared. So you take one lens and that just kind of gets you your broad spread. And then you take the middle lens and you kind of bend the closer to infrared into the center, but now your purples and your ultraviolets are bent out. And then you put the last layer of glass in your third one, and all it does is it bends the outermost in. So all of your colors come to a point where your imager is. So that's what you want to make them out of ED glass. But when you get to the third element, there's actually even a different kind of glass called fluorite glass. That's why the Takahashi 3-element Apo is so expensive. Is if you've got a 5-inch piece of fluorite glass, that's an expensive thing to make. Tight production controls on the glass elemental composition to make it bend all of those purplish colors to the center. If you ever look through the Brandon refractor at Fox Observatory and you looked at something bright like Jupiter or the moon, it has a purple halo around it. You can actually buy an eyepiece filter that will be that third element that the telescope is lacking. The Brandon just has 2 lenses, the doublet. It pulls in certain, but the purplish stuff is left out. And you put an eyepiece filter on, it will bring that in. So that's what ED is. I think it stands for extra dispersion, which you would think it's just the opposite of what you want. You want tighter dispersion, but ED. How many think that the smart telescope market is kind of rapidly adding features while dramatically reducing price? I know not a lot of us own personal telescopes. I own too many. But I will say that when this Celio comes out and is actually being produced, I would have a serious discussion with mods about, I'm not going to say I would donate one, but my first impulse would be, you can be on the air for $500. Don't you want to have that? Because your NASA STEM budget's going to get cut short, so there'll be less STEM opportunities for the museum to make side revenue. But by bringing a telescope out to schools and putting a white light solar filter on it and showing them sunspots in the daytime as it only costs you $500, telescope plus a tablet, you're there. I think that would be interesting. But then I always thought years ago they could put a smart scope in it, mods, and just always have a big screen TV. This is what the telescope's looking at right now. We'd have to have somebody who knows astronomy to operate it all the time. I guess until Helen came along, not everyone that was at mods was a subject matter expert on amateur astronomy. Any other comments or questions? Otherwise, I'll stop recording. Yeah.